Hi. I'm here to present, as you just said, the video game description language environment for Unity machine learning agents. And these are my co-authors. You can find it on the bottom link there. I'll show that later as well. I'm a game developer and a game designer from Copenhagen. And I recently also became a PhD fellow. And that is what happens when you ask Photoshop to autofill your face. Here's what I'd like to leave you with. I'll be talking about how I brought the video game description language to Unity, as well as my motivations and future potential for the framework. First of all, extending the VGDL family of languages, programming languages opens it up to new and larger groups of possible users. This, combined with the fact that Unity VGDL incorporates Unity machine learning agents, makes VGDL available to more hobbyists and game developers who are less inclined to engage with the Java framework. Unity VGDL is also a first step towards generating actual Unity prototypes from VGDL. So the three images here on the right would show a possible progression from like the old PyVGDL framework to GVGAI to something like this weird game I found. It's called Cube Puzzle 3D Juicy Fruit. Now, does anyone not know what VGDL is or how it functions? One person, good. So VGDL is a small description language which is comprised of 4 different sets. You have a sprite set. This set is basically determining what sort of game objects are in your game. There is an ontology behind it where you can select different types of game objects. So here we have there's an immovable game object, which is just something that doesn't move. There's a flicker, there's like some avatar types. And then you have a level mapping set, which maps from the level, which you see on the top right, the level description, to which objects are going to be spawned in specific grid positions. You have an interaction set, which basically determines what happens when 2 things collide. There we also have an ontology and a set of collision effects, so killing one of the sprites or collecting resources, etc., etc. And then lastly we have a termination set, which determines when the level is over. And these two, the game description and the level description, are combined in all of the VGDL frameworks into playable prototypes like the one you see in the bottom right. So I created Unity VGDL as a port of the Java VGDL parser and engine, and it follows the GVGAI ontology. If anyone doesn't know what the GVGAI is, it is the General Video Game Playing AI framework. It's the competition framework that encompasses the Java VGDL. The Unity VGDL works with all the single-player games available in the GVGAI examples. There's about 120 of those. And it contains, so we've also defined it with roughly 10 pre-made scenes that you can use for various purposes, depending on whether you want to train or you want to test out your agents, or you want to play it yourself. And they work out of the box, so you can just load them up and change whatever game you want, and it should load it up and run it. Early on, Unity VGDL actually generated Unity game objects at runtime and spawned the entire hierarchy every frame, and it managed to run at 60 FPS, which I find amazing. But later I changed it so that it just renders directly to your render texture, and it vastly increased the frame rates possible. But I did encounter the issue of integrating with ML agents, because ML agents did not support anything but visual observations from a camera, so I had to suggest and implement a change to their framework so that they could also accept render textures. And luckily that was included in their version 0.8. Speaking about ML agents, a quick recap for those of you who didn't attend Erwin's talk on Tuesday. And Unity ML Agents is a machine learning framework. It's got a Python part and a C# part. They set up a training pipeline when you train between Python and C#. And when you're done training, you can run your C# part in inference mode and just do model inference that way. That makes it possible to run on all the possible platforms that Unity supports. When you need to set up your ML agents inside of your Unity scene, you set it up with an academy and some agents. The academy you set up to basically handle setting up the learning pipeline or the inference for all the brains. And the agent is in charge of collecting observations and executing the actions that a brain selected. Brain here is a neural network. So here's an overview of how ML agents and the VGDL implementation work together. First we have the VGDL Academy. Here noted the ML Academy. Things on the left of the dotted line there is the ML agents part of the framework, and things on the right are all the VGDL parts. The Academy specifies which game to load and instructs the VGDL agents to use their respective runner to load it up, parse it, etc. And whenever the VGDL agent needs a visual observation, the VGDL renderer can be instructed to render the current game state. And the renderer can also be set up to just render directly to the back buffer, which means directly to the screen, in case of human play or demonstrations. Here, I've forced a random agent to suffer a bit, if you're talking to that, and play through each single-player VGDL game to verify that all 120-ish games work. And that is all of the continuous physics and all the grid physics games in Unity VGDL. But we don't have to look at this because we control this reality. So, Unity VGDL training. There's two ways to train. You can either train in editor or with executables. When you train in editor, like I've done here in the top, I've selected the 4-instance scene. We have created like several scenes. There's one with 1 instance, 2 instances, 4, 8, and 16, I think. 16 one runs horribly on this hardware, but it's there. There, I've set it up to run with 4 instances of Sokoban. I've added all 5 levels into the training curriculum that you can see on the far right. And that's just a simple way of defining which games to load. ML agents themselves has like a curriculum system that is far superior to this and can be used if you generate several executables. You can set it up to learn progressively harder tasks. And speaking about executables, you can generate an executable by simply selecting it from the list of scenes when you build. You build it and then you run it with your with the Python interface. And there you can spawn as many instances of your executables as you want. And that's just to fill up or to use fully your the CPU cores you have available on your training machine. Okay. We did a few experiments with the VGDL examples. We used the games. We used 4 out of the 8 games that Torado et al. Selected for their test of the GVG AI learning track. The 4 games we selected were Aliens, Boulder Dash, Wait for Breakfast, and Zelda. And we used the default training parameters from ML agents to train with. Here's our results. You can see in the top there that we have 1 instance, that's the blue line, and 8 instances, that's the orange line, training for 1 million steps per instance. The graphs are automatically output to TensorBoard from the ML agents framework during training. And you can see here in table 1 that training a single instance for 1 million steps provides only a small improvement compared to random, but with 8 instances we see similar results to the A2C baseline from GVG AI Gym. The reason for our scores being slightly different with more decibels and stuff is that Torado et al. Actually reported the maximum mean scores during training, whereas we used the average score of over 20 runs after the training completed. For future work, we're missing a few features, 2 players, and also showing a bit more of the training state. And the ML agents framework also allows you to easily enable a memory module and a curiosity module, and you can also tweak the hyperparameters, and we've done none of that. So there's a lot to be done here. And the last point here is what I'm really interested in. Making Unity prototypes from VGDL descriptions VGL could be a very useful prototyping tool if we actually made real prototypes from the VGDL descriptions. So that's what we are going to be working on at our place soon. Oh, and a bonus feature, you can combine level descriptions and game descriptions into one in this parser. It's a small change, so I added it. It's not used, but you can just use it if you want. Unity VGDL adds another set of environments for ML agents research that is still fairly small, and maybe a few lost souls from like the Unity developer community will stumble upon it as well and try it out. But really, Unity VGL is a step towards making VGL more useful for game designers who want to prototype for human players. One of the benefits for creating better prototypes that we see from other tools such as like PuzzleScript or OmniLudicon is that a community of developers that actually want to engage with it create a large amount of prototypes that you can then do research on. So if we changed VGL slightly to be more user-friendly, we would hopefully get a bigger set of games that we could work with. And Unity VGL is available on GitHub. We welcome contributors to come help us finish the missing framework, the missing features, and we encourage you to use it for research and for fun. That's it. Yeah.
I think it's really, really nice work. One question. So, do agents, and I know it's not the standard ML agents in Unity approach, but is it possible that agents have access to a forward model and still run within Unity?
Actually, so there's a thing called the heuristics brain, I think, where you can do scripts, and I've implemented the forward model, so it's already in there. And those two should be able to connect.
So it should be possible to have these lovely prototype games and also have statistical forward planning AI to give us like immediate working AI.
It should be. There might be, you might have to tweak it a little bit in order to make it work, but it's very close to having that implemented as well.
Interesting.
So with your heuristic brain and Unity,
Yeah.
with the heuristic brain, you are free to implement any algorithm evolution. That's the point of it.
Yeah. The main problem is that connecting the internal forward model of the VGDL engine to the heuristic brain of the ML agent system. But it's very close. You can probably do it. It shouldn't take too much work.
I mean, it's open source.
Yeah.
Yeah, it may be open source, but you still have to do the copies of the current game state and advancing it quickly enough. So it's one thing to be possible in principle.
Right, but that's actually in the part that I imported from Java. That already has a forward model, and the forward model is already in there.
So it really should work.
It really should work. There's just like a tiny connection thing. That's, yeah.
So using GVGA engine is not particularly fast. Do you have any idea if this is faster or how fast it is in general?
How fast is GGI Jim? Do you know?
I've just heard that it's not fast.
Not fast. This I ran in an 8-instance setup. I ran took around an hour to compute 100,000 steps on this computer. So I don't know if that's faster or slower, but that's.
But Chris Stanford has just made it fast. That's all.
Exciting.
It's a race.
It's a race.
But is it editor or as a standalone?
That was as a standalone, yeah. And it actually depends on which game you're doing, because like the more rules you have to stuff. Yeah.
Are you building it as Unity game objects, or is it like?
No, as I said, I did that originally. But building it as game objects was just like spawning a game object and slapping on a sprite. So it wasn't really a game object. That's the thing we want to do now. Is we want to make it into actual game objects that when they collide inside of Unity, like Unity drives all the logic, then it does the effect. Yeah.
Thank you.
For generalized framework for self-pay trading.
Thank you.
Oh.
Oh, that's better. Do we have a clicker? Like some people had it. It's okay. I can do without it. Well, hello everybody. Here to tell you a little bit about self-pay training, which is a word that's come up quite a few times here. I'm not the only person presenting this work, so I thank everybody. Some of them are actually in the room who helped me actually come here to give this one talk. So some of the definitions are gonna be a bit hand-wavy, and I do welcome that if you find this intuition and motivation interesting, you actually dwell down into the paper in which we have, in more principled ways, defined all of the topics that we're gonna discuss here. So we'll start with the multi-agent problem. And so in reinforcement learning, especially multi-agent reinforcement learning, you have this multi-agent reinforcement learning stack in which on one side you have the environment, and then you have agents living in this environment, and then the agents, you can treat them as a black box, that they may be fixed, they may be learning, you don't really care that much, and then you have the training scheme, which is essentially what do you do so that the agents, essentially how do you control not the actual environment, but how do you control perhaps which agents are playing in the environment at what time. And then there's many different training schemes in multi-agent reinforcement learning. So, for instance, if you want to train a single policy to be really good in a multi-agent environment, maybe you can use an existing policy to train against, and so you essentially will get a policy which is good against an existing policy. But maybe you just made a game from scratch, and therefore you don't have existing policies. So well, that's not too good. So maybe you can perhaps distill a policy from an expert moveset. So you have chess, and maybe you don't know how to Google that much, but you know how to get so you don't know how to get an existing policy. But maybe you can get a data set of expert moves. But again, if you maybe make a game from scratch, you won't have an expert move data set. If you are not using GPG AI, well, if you're using GPG AI, cool. But if you're not, then you may not have an environment model, which is a shame. So you can't even use something like MCTS, and you can't even do maybe like something like the expert iteration framework that AlphaGo uses. So you can't bias a policy towards essentially towards what MCTS would do. So there's a lot of restrictions that can take place in life, and so if you can't do any of these three, then what can you do? You can do self-play. You can just like get a very bad policy and just get a very bad policy to beat itself. And because it's a very bad policy, then you don't need to be that great, and then you can just iterate on that, which is great. The thing is that self-play actually is a very hand-wavy term it's been around for quite a while, but it's actually never really been formalized. So then I went down into the literature, and I went 60 years in the past to Samuel, which is actually the first person that coined both the term self-play and the term machine learning. So he's a bit of an important guy in this field of ours. So 60 years ago, he essentially got a policy, well, he essentially got a one-ply tree search, so a tree search mechanism that only looks one step into the future to essentially play checkers. And it learned a state value function by playing against itself, by simulating that the policy that the opponent was using was the same policy that they were using. And he called this training method self-play. So then, fast into the future, the TD-Gammon algorithm used the temporal difference learning to essentially play against itself using self-play to get a really good policy that turned out to be able to beat professional players in backgammon. So this guy showed, this right honorable gentleman showed that you can actually get self-play to actually reach professional level. So just beyond amateur checkers, as Samuel did, because 60 years ago computation was scarce. So TD-Gammon showed that actually you can do this in really high level. And as we all know, David Silver, another really brilliant scientist, actually managed to extend, to use self-play and a bunch of other things to beat the best Go player in the world. And self-play hasn't been just confined to to board games. There's also this paper from Bansal from OpenAI that actually did robotic simulations in which essentially they learned through self-play to tackle a variety of tasks. It's interesting, or rather frustrating, when you're actually reading the literature, that each person seems to have their own little definition of what self-play is. And that's infuriating, because at some point you want to actually see how different self-play mechanisms actually compare against one another. But nobody's really formalized, and nobody's really created any sort of notation that allows you to, in a more principled manner, compare one against the other. So that's precisely what I set out to do. I went out into the literature and tried to define a mathematical notation that allowed me to define all of these different self-play algorithms, or self-play training schemes, as I like to call them. So the motivation is what I just said. There's not a sheer mathematical notation that doesn't allow us. There's not a mathematical notation that allows us to formally compare them. And therefore, after a lot of thinking and a lot of going up to the whiteboard late at night, I came up with two assumptions that seem to be followed implicitly or explicitly by everybody that ever quoted self-play as a training scheme that they were using. And they're actually very they're very common sense assumptions, but it's nice to actually have them written down and stated that this is something that we are assuming. The first one is, well, rather simple. The fact that the policies that are present in the environment are either the latest policy that you're using or previous policies previous checkpoints of the policy that you're using. So essentially, if you've taken 1,000 updates for your policy, it's okay to call your algorithm self-play if you play against a policy it's okay if you play against your policy when it only had 200 updates instead of 1,000 updates, which may be the current one. And the second one, it's more for technicalities when you're actually coding this up, and this actually has some nice repercussions for future work, but it's essentially, it just says that you are allowed to change the policy of other agents in the environment. So if I'm using self-play, naive self-play, in which I play against the latest version of myself, then it makes sense that it makes sense that if I update my policy, I also update the policy of other agents in the environment. So with those assumptions out of the way, we formalize self-play, we create a self-play framework by formalizing the following notions. The first one is the menagerie, which essentially is very similar to the notion of archive or elite from the evolutionary algorithm from like notation, in which it's essentially a set of policies from which it's a set of policies that from which you can it's a set of policies from which you can sample policies to then populate the behavior of other agents in the environment. So it essentially says policies from the environment must come from policies that live in the menagerie. The next notation is this notion of a policy sampling distribution, which is essentially a function that, given a menagerie and given the current policy that you're actually training, because remember the goal is to train a policy for a certain multi-agent environment. So given a current menagerie and a current policy that you're actually training, with this policy sampling distribution will decide on which other agents will populate the environment, or rather which other policies will populate the agents in the environment. And finally, we have the gating function or curator of the menagerie, which essentially, given a current menagerie and given a current policy, it decides whether or not to include the current policy into the menagerie, so whether to make a checkpoint that will live in the menagerie, or whether to curate, or whether to essentially drop certain agents from the menagerie. And so don't be scared by the next slide. Oh, sorry, that's not the next slide. Anyway, so and the reason why this is a framework is because by choosing a different initial menagerie, choosing a different policy sampling distribution, or choosing a different curator, you can actually come up with different self-play algorithms. So what this means is that and I'll show this later on, for the different notions of self-play that different researchers have come up with throughout history, using this framework, this is actually a rather simple framework, it just contains 3 little things. You can actually represent the different algorithms that they've created, which means that with this notation we now have a more principled way of comparing different self-play algorithms, which is great. So, boom, a lot of math. You don't really need to look too much into detail, but this chunking here is essentially the classic reinforcement learning loop. You get an initial state, and then until you finish, so you start an episode with an initial state and observation. Actually, I make this for partially observable environments just to make it more general and slightly more confusing. It makes the reviewers think that I know more than I actually do. So yeah, you start with an initial observation and state, and then for a given policy vector, so this contains the policy of all of the agents in the environment, you essentially sample actions, and then you get the next state and reward, and then etc. Until you finish. And then the 3 things that I mentioned before, so the policy sampling distribution of the curator and the menagerie, so how they actually fit into this multi-agent reinforcement learning loop is that at the beginning of an episode, you choose, so you sample using the policy sampling distribution, you choose which other agents will populate the environment, and then the agents that live in the environment will be the policy that you're training plus the other agents that you've sampled. And then after the episode, the curator will decide whether or not, so the curator will decide on the next, essentially the next iteration of the menagerie. So we'll decide whether or not to make a checkpoint of this agent to be included in the menagerie, and whether or not some elements of this menagerie should actually be dropped. And I promise this is like the most mathematical slide in the whole thing. Now the pretty pictures start coming. So given this, then let's actually define under this framework some of the self-play algorithms that live in the literature. And spoiler alert, they are all very simple, and it is my well-intentioned hypothesis that there's actually like a lot of self-play algorithms that we haven't even like conceived yet. So naive self-play is very simple. It essentially says you shall only play against the latest version of yourself, and therefore the policy sampling distribution essentially just says put all the probability mass on the latest version of yourself and nothing else. And the curator doesn't really. The curator just essentially just takes the latest version of the policy. It doesn't even look at the menagerie. So yeah, one of the most used self-play algorithms out there. It's essentially the simplest one you can get, which is interesting. Others have actually relaxed the assumption that have relaxed the initial assumption of self-play that you can only play against the latest version of yourself, and instead. Have come up with this algorithm that I've named Delta Uniform Self-Play, in which essentially says that the gating function will be fully inclusive. So with every policy update, and this can be due with hyperparameters, but just for simplicity, with every policy update, you're actually gonna include that into the menagerie. So your menagerie is gonna contain every single policy that ever was in your training, and then the policy sampling distribution will uniformly sample from all of the policies in your menagerie, and then you have a tiny hyperparameter here that determines whether you sample from the full history. If this is 0, maybe half of the history. If this is 0.5, and then if this hyperparameter actually becomes 1, then this is the same thing as naive self-play. So this can be conceived as a rather like a further step from naive self-play in which you actually sample from all of the previous versions of yourself. So this next slide that I'm going to show is a wild speculation, so don't quote me on this, but I got this information by, well, reading a lot of papers by DeepMind and actually getting a pretty nice conversation with David Silver when he came here on Tuesday, which is how to define their training scheme, what that they call Alpha Star League, under our framework. And we shan't get into some of the details as to how to compute certain things, but let's just say that in their the Alpha Star League can be captured under this framework by essentially saying the policy sampling distribution will compute a Nash equilibrium over the existing policies in your menagerie. So, well, without really getting into much detail as to how you compute a Nash equilibrium, this essentially says, given all the policies of your menagerie, if you're playing against another person that also has access to all of the policies in the menagerie, then with what probability should you choose each policy, such that when you play against one person that can also choose the same agents as you, like what is the optimal? I'm getting a bit off topic, but essentially, yeah, the Nash equilibrium over the menagerie. I'll happily take questions on this later. And then the curator function, so the thing that decides when to create a checkpoint. 1 minute left? For real? Sure. Okay, so that's cool. Qualitative metric, does this even matter, like, at all? Should we even care about this? And we say, okay, let's actually figure that one out. How about we get like trajectories from essentially, you train an agent and you get all of the trajectories and you embed them in a 2D space because people like visualization. And then, so for the game of rock, paper, scissors, you get like, this is playing scissors, this is playing rock, this is playing paper. You put a lot of trajectories that you embed into this 2D space. And then, so let's actually, if the first 500 trajectories, this was the median, and now with the, from episode 500 to episode 1000, this is the median. Let's actually see how our training progresses. So started playing a bunch of paper, and then started playing closer to scissors, and then started going closer to rock. And this makes sense because if it's this is actually for full history self-play. So it's playing against it's uniformly sampling all of the previous agents that it was. So it started essentially only being able to play paper, and then it started playing scissors, and then it realized that if a lot of scissors was being played, then rock rock should be played. And then at this point, we have agents that play both rock, papers, and scissors, and we see that this can go on and on and on. And then 1 eternity later, after training finishes, we see that we've actually converged to something that looks like the Nash equilibrium, which in the case of rock, paper, scissors is playing rock, papers, and scissors with equal probability. And we actually see that using different self-play using different self-play algorithms, we actually get different trajectories. We get different trajectories over this visualization of the joint policy space. I should have specified this was the joint policy space, but I only had a minute. And yeah, so future work is, can we go crazier in our self-play framework? Can we create some quantitative metrics to actually, in a more nuanced way, compare different self-play algorithms? And also compete in the, thinking about the computational cost, because things like computing the Nash equilibrium can actually be rather expensive. Thank you very much. Questions?
Thanks, Tim. I think it's really interesting work, but I'm just not sure about the name. So, to me, as soon as you go away from what you call naive self-play to having a menagerie of agents, essentially, why is that still self-play?
So, that is something that used to keep me awake at night until I embraced the name. And it's, I call it self-play because I don't think, so the self, to me, doesn't come so much from the policy, but rather, so I take a step back as somebody that is actually coming up with a training scheme. So to me, the agent is an external thing. So self-play just means like policies that I've created myself. So this is no...
So for example, if you do co-evolution to evolve game players, within your framework, would that also be considered self-play?
I'm not too familiar on what co-evolution means precisely in this scenario, so I wouldn't really be able to tell, but I'm happy to have a conversation later.
Okay. I mean, I think it's a very nice framework.
Thank you.
Yeah, this looks a lot like what a buffer or an experience replay buffer is. And so could we imagine like meta agents that would deal with all that? Like
Yeah, so...
evolutionary algorithm or reinforcement learning algorithm?
So actually, some of the future work that we want to develop, but we're still figuring out how to do it, is could you perhaps learn for a specific given environment? So we assume that for different environments, we will need different policy sampling distributions and different curator functions. So it would be nice if we can actually learn as training progresses which policy sampling distributions are curator functions to use. And yes, for that, we could use meta reinforcement learning to then choose which agents to actually use to populate the behavior of other agents in the environment. Sorry if that didn't fully... Oh, nice.
Okay.
Well, thank you very much.
Yeah, thank you. And for last presentation, the main explore or customizable 3D benchmark for assessing generalization in reinforcement learning.
Very cool. So.
I'm really excited to present to you Maze Explorer, which we built at the Game Intelligence team at Microsoft Research up in Cambridge. And it's a 3D environment for assessing generalization in reinforcement learning. And one of the cool features is it's ridiculously fast. So there's loads of different reinforcement learning environments, and you use them for loads of different things, such as self-play, or maybe simple environments such as cart pole and pendulum for assessing whether algorithms are actually working in the first place, to more complex environments such as Space Invaders and Majoko for, say, continuous control. And pretty much all these environments have converged on this GIM interface, where you create the environment and then you define in Python a step method and a reset method. And so the reset method, when you call it, it sets the game back to the initial state, and it returns an observation. And you use that observation, the agent then decides which action it's going to do, which it sends in the step, and then it gets the reward in the next state. And it keeps on stepping till it plays the game. But one of the, so in our task we were wanting to explore a maze, and this is built on VisDo. And so what you do with reinforcement learning is you give it a reward with lots of these keys, and you train it to run around and try and hunt for these keys. And so we're training it purely from the visual pixels on the screen, and you can see the nice trajectory on the right of as it goes and picks up all those keys represented by stars. But what you find is when you then give it a map it's never seen before, it completely fails. And so what you think you've done really well at, which is learning to navigate in a maze, you've actually not done so well. And so normally you see these lovely pictures people have in their papers which shows the learning curve and over time, and your kind of reward increases and then it converges. But as soon as you give it a maze or an environment or a slightly different setting than what you've seen before, then it fails. So here's 10 by 10 maps, so the same size, it does a bit worse. And then as you increase the size, it does considerably worse than that. And so one of the things is you're basically training on your test set. And we know this in standard supervised learning that you need to split it up so you don't overfit. And there's been a couple of really cool examples of prior work where they've worked to try and overcome this problem. And so in DeepMind Lab, CoinRun and GVG AI, you can define either slightly different environments for training and tests, or you can actually have completely different games and see if you can generalize across them. But one of the things we wanted was doing it in 3D, really installable and really quick. And so that's why we decided to build Maze Explorer. It's really configurable, so when you define your environment, you can say how many maps you want, the different size of these maps, whether you want to randomize the spawn locations, how many keys, where are these keys, and the actual complexity of the maps themselves. So you can start with a much easier task, like just training on one map, evaluate on it, have the keys in the same places, start it with very small, and you can get up to 2,500 frames per second, and then you can scale it all the way up to like massive mazes, doing it in completely different tasks, with pixels and textures you've never seen before. And so it makes it really easy to create these separate train and test maps, and then, as I said, you've got the standard reset and step interfaces that we love with GIM. So, as I mentioned, few of the benefits, it's incredibly lightweight, and so again, really easy to parallelize, really customizable, and really easy to install with pip. So here's one experiment we did where that classic problem of if you train on one maze and show it in a maze it's never seen before, it fails, you can solve with domain randomization. And so purely through the config of how we set up the environment, you can get much better performance. And so the graph on the right shows you that the kind of little blue bar to the left shows the performance of a random agent, and the orange bar next to it is if you train it in a fairly naive way, just kind of one map and one single spawn position. And then as you combine multiple maps, it does a little bit better, or with random spawn, it does a bit better than that. But when you've got both, it has a much greater performance. And so here's a little video of our agents running around, and there's just one function to call to then actually create these videos of your trained agents running around. And so in the bottom right is our best agent, which is training with multiple maps and random spawn. Top left is random agent, and then there's the ablation of the two. And this is using a PPO agent, and it's not got any memory, which is why you see the little stutters occasionally. And so, thank you very much. It's all on GitHub, and we're continuing to add new features. So one we've recently added is every time you call reset, it generates a completely different maze it's never seen before. And yeah, thank you very much.
There was something that said data augmentation.
Yeah.
Could you talk a bit about what that is?
Sure. So there's a couple of different ways which, if you're trying to get generalization, you can try and do. One of these is these drop blocks. So you basically draw random colored squares across your map. And what it means is you don't overfit to the exact pixels or textures on screen. And so the Coin Runner paper has a really nice example of how this increases performance. And another thing linked to that is in reinforcement learning, pretty much most of us don't use dropout layers or batch normalization because they decrease the performance. But what they show is it actually increases your performance on unseen environments or unseen scenarios, which is kind of what you'd expect.
I might have missed it. You said in the beginning our L system often generalized well in mazes. So did you then found a solution that it better generalizes in your approach?
So our kind of novel contribution is more the environment you can use to separate these training and tests. And it shows that it normally doesn't do very well if you just train it on one maze. It will actually overfit to, say, the exact key position within that route. But then if you, say, add in this domain randomization with the different mazes or stuff such as the data augmentation, then it actually improves the performance. I maybe went a bit quick on that.
But you could not solve it from 10 by 10 to 20 by 20?
No, so it increased the performance doing these, but it didn't solve it completely. Another challenge which we were unable to solve, which is left as a challenge for the community, is if you just train it on one set of textures and then give it a set of textures it's never seen before, the majority of algorithms fail at this. And so there's some really nice overlap is if you're wanting to, say, train on simulation then deploy to real world, you actually want it to be really immune to these different changes in textures.
Okay, I have one question. Can you make some the easy levels of maps, and can you increase the complexity of the map from the customization?
Can you as the Python program? Yeah.
Oh, okay.
Yeah, exactly. So you can fully define what the complexity is and what the sizes are. One of the nice things is, so VisZoom's fantastic, but quite a lot of the mazes you have to generate manually with a kind of GUI maze creator or GUI game creator. Or you have to define your different rewards and everything through their custom DSL. And so this brings it all to kind of the Python level of you can just say what you want.
I guess my question is, can you change sort of the game goal of the map? So one is capture the key, and the next one maybe you have to, I don't know, kill someone or something like that.
So it's built on Doom, and as you saw in the video, you can get a gun and shoot. We don't currently at this task. Some of the other statistics you can get from it are kind of like raw coverage. So again, if you're trying to do these exploration side, that wouldn't be much work if you kind of use the VisZoom scripting language to add back in the enemy and set that as the reward. Definitely makes for some more interesting videos as well.
So I was just wondering, do you have like preset, I want to say scenarios, but not really scenarios, but like challenges that, where say for example, if I'm creating an agent, you're creating an agent,
Yeah, so we've got a, in this one here, we've got the easy, we've got, so, slightly out of order, but we've got an easy, medium, and hard set, and we've got both 10 by 10 and 20 by 20. And so you can train in a variety of different ways and then kind of post your benchmark score for those different sizes. Yeah.
Just a follow-up question, do you have randomized textures, or is it just a set of textures?
So there's a set of textures, and you can either manually say which specific one you want, or you can say to randomize the different textures. And so you may want to say select one for training, and then kind of randomize from the others during testing.
Okay, thank you very much for